In the last video, we talked about vector spaces and the 10 rules that are necessary for vector spaces. Now we'll start looking at subspaces. So suppose I have some vector space. Let's call that vector space V. Then I'm going to introduce a subspace. So I'm going to start with it being a subset. Call that subset a W, so it's entirely contained in vector space V, and it's non-empty. Right? So W is a non-empty subset. W is what we call a subspace if it has two properties. If its properties are closed under addition and closed under scalar multiplication. If those two properties hold on everything in W, then W is a subspace. It's always a subset, right? It is always a set that's inside of a larger set. But is it a subspace? Well, it depends. If the elements in that set are still closed under addition and scalar multiplication, then it's a subspace. If it's not, then it's not. The other ones in there, like the commutative, associative, distributed, those will still hold. And because it's a subspace of V, those properties are already carried over into that smaller set. But closure under addition and scalar multiplication is not necessarily so, because you're only taking part of that big set. So if you want to look at it like this, suppose you've got set W as a non-empty subset of vector space V. So in other words, I've already verified that that thing is a vector space. It's not just a random set. I've already verified that thing is a vector space. Then W is a subspace of V if and only if these things are true. You realize I did not misspell the word if. Putting two F's there is saying if and only if. So it's that A implies B and B implies A type thing. So here's the two things that have to hold. If vector U and vector V are in that subset, then the sum U plus V is also in that set. And if that vector U is in that subset and C is any scalar, then C times that vector is in that other set. If that's true, then it's a subspace. If one of them fails, then it's not. There are a couple of special ones. I could look at this, and that's called the zero subspace. So the set that only contains 0 is the zero subspace. Add 0 plus 0, and you'll get 0. Multiply 0 by any scalar, and you still get 0. So 0 is its own subspace. The entire vector itself is also a subspace. But neither of these are terribly interesting subspaces, right? The vector of just 0 and the whole set itself. So we call these the trivial subspaces. All of the others are called either proper subspaces or sometimes you'll simply call them non-trivial subspaces. All right, so the two trivial ones are the zero subspace and then the entire set itself. So let's look at all the possible subspaces of R2. Okay, so possible subspaces of R2. One of them is the trivial subspace, or atrivial subspace, and I should say is the zero vector. Another one is all of R2. So I'm kind of being cheap and putting the two trivial ones as their own lists. All right, the third one is the set of all lines that go through the origin. Because I need the zero vector in there somewhere, so that will come from the bigger set itself. So possible subspaces of R2 include all the lines that pass through the origin. You can do this for R3 also, right? Except this time it would be the 0 vector would be 0, 0, 0. You'd have all of R3 as another trivial subspace. And then instead of the set of all lines that go through the origin, you would have the set of all planes that go through the origin. Those are also subspaces of R3. So let's look at a couple of these and see whether or not these things are subspaces. So suppose I have W defined this way. Here's how you'll see this defined somewhere. XY such that x is greater than 0, y is greater than 0. Is this a subspace of R2? Well, if I add numbers together, so I have to check under addition and under scalar multiplication. Under addition is fine. If you add a positive value plus a positive value, you'll get a positive value. So that's okay. What's the issue with scalar multiplication? Well, suppose my scalar is -1. Well, I pick some xy that's in that subspace, that set, and I multiply it by -1. Now I come up with the vector -1, -3. This is not in W. W only contains values that are positive for both the x's and the y's. And so is it a subspace of R2? No, it is not a subspace of R2. All right, let's try another one. Let's suppose that I have expressions in the form of p of x equals a sub 0 plus a sub 1 times x plus a sub 2 times x squared until I get to a sub n x to the n. So these are polynomial functions where the a sub n's are real numbers. What do I have to check? I only have to check two things because the set of all polynomials is already a vector space. So the only thing I have to do is check closure under addition and closure under scalar multiplication. So let's check first for closure under addition. Suppose I've got one polynomial that's already up there, and I'll come up with another polynomial. I'll call it b sub 0 plus b sub 1x plus b sub 2x squared till I get to b sub n x to the n. All right, what is the sum? P plus q is going to be a sub 0 plus b sub 0 plus a sub 1 plus b sub 1 times x, a sub 2 plus b sub 2 x squared, until I get to the very last term, a sub n plus b sub n x to the n. Yes, this is in that form that we want, right? Same form. It's a polynomial. All right, how about under scalar multiplication? So now let's check scalar multiplication. Suppose I take some scalar times p of x. Then I would get what? I would get the scalar times a sub 0. I would get the scalar times a sub 1. I would get the scalar times x. Scalar times a sub 2 times x squared, all the way till I got to the scalar times a sub n x to the n. Is this also in the form of what I have here? Yes. That means that that polynomial is a subspace. Okay? So are expressions in that form a subspace? Yes. They are closed under addition. They're closed under scalar multiplication. All right, let's look at another one. We'll look at something in R2. What if my subspace was defined this way, as x comma 3x, where x is a real number? That's what that notation means. X is an element of the set of real numbers. My question is this a subspace of R2? I could look at this in number terms first if I'm not entirely sure. Suppose I had a vector 1, 3 and a vector 5, 15, right? You realize both of these vectors would be in set W. because the second element is 3 times the first element. Let's check addition. If I add them together, 1 plus 5 is 6, 3 plus 15 is 18, and yes, I still come up with a vector whose second component is 3 times the first one. How about under scalar multiplication? If I had some scalar times 1, 3, then I would come up with C, 3C, and sure enough, it's still in the form where the second vector is 3 times the first vector. If you want to do it more thoroughly, you could come up with vector A, 3A, and vector B, 3B, and show that adding them together will give you the vector A plus B, 3A plus 3B. Well, 3A plus 3B can be written like that, and sure enough, it's closed under vector addition because the second element is 3 times the first element. Is it closed under scalar multiplication? Sure. Multiply a scalar times the first one, and you get CA and then C3A. So the second one is 3 times as big as the first one. All right, let's look at another one. Let's look at W defined as vectors in this form, x, 3x plus 1, where the x's come from the set of real numbers. I could try this out with numbers, right? I could try this out with 1, 3 plus 1 is 4, and then let's make it easy and choose 2, 7. Right, if I add these together, I end up with 311. Is that something in the form where the second element is 3 times the first plus 1? Well, 3 times the first plus 1 would give me 10. No, that's not equal. So W is not a subspace. It fails closure under vector addition. I could do a more general case of this, right? So if I were to write a proof, I wouldn't write it with just those individual values. I would try to give a more general case. So suppose I had the vector A, 3A plus 1, and the vector B, 3B plus 1, right? That fits vectors in the form of second element is 3 times the first plus 1 more. Let's check vector addition. This will give me A plus B, 3A plus 3B plus 1. Well, what do I want? I want 1 more than 3 times the original element. Well, 3 times the original element, actually this gives me 3A plus 3B plus 2. 3 times the original element is 3A plus 3B plus 1. But what it's actually producing is 3A plus 3B plus 2. And now you realize here, this answer was 1 more than what would make it an actual subspace. So is this a subspace? No, it's not a subspace. It fails under vector addition. I bet you it fails under scalar multiplication also, but really, I just showed it under vector addition. All right, let's look at another case. Is the unit circle a subspace of R2? Ooh. Is the unit circle a subspace of R2? Well, what is the unit circle? The unit circle is the set of all the x squared plus y squared equals 1s. So let's take 2 points on the circle. 1, 0 is on the circle. 0, 1 is on the circle. Let's find the sum. The sum of those two vectors is 1, 1. 1, 1 is not on the circle. So is the unit circle a subspace of R2? No, it's not closed under vector addition, so it's not a subspace of R2. All right, how about going back to some calculus concepts? In calc, you know that if you have two continuous functions, right? So if you have f and g as continuous functions, then f plus g is also continuous, and a scalar times f is continuous. So those continuous functions are a subspace. And so you could say that the set of all continuous functions on the interval from negative infinity to infinity is a subspace of all functions from negative infinity to infinity. Right? You could also look at it this way. Suppose you had two functions that were differentiable. Well, the sum of two differentiable functions is also differentiable, and a scalar times a differentiable function is differentiable. So the set of all first derivatives of continuous functions on the interval from negative infinity to infinity is also a subspace. So you could start drawing yourself these Venn diagram type graphs that detail the subspaces. So suppose you start it with all the functions on the interval from negative infinity to infinity, right? All the functions on the interval from negative infinity to infinity. This set of all continuous functions is a subspace of the set of all functions. So the set of all continuous functions from negative infinity to infinity is a subspace of all the continuous functions. And the set of all continuous first derivatives is a subspace of that. And you can keep going from there. You'll find sets of continuous second derivatives and so forth and so on. Let's wrap this lesson up with a little proof, because we haven't done too many proofs yet. I don't know if we've done any proofs yet. And proofs are an interesting and important part of this course. So let's look at this theorem. Here's my theorem. If I've got two sets, set V and set W, and they are both subspaces of some larger group U, then the intersection of those two sets is also a subspace. What does this look like? Suppose this is set V, and suppose this is set W. Where is the intersection? I'm claiming that that intersection itself is also a subspace. So how do I do that? Well, the first thing I'm going to do is I'm going to pick two vectors that are in that intersection. All right, so I'm going to choose vector 1, vector 2 in the intersection of V and W. Both of them are in V. So I'm writing out sort of the sketch of this proof. You would write it out nicely with capital letters and periods at end of sentences. So both V1 and V2 are in V. So that must mean because V is a subspace, the sum is also there. So V1 plus V2 is in V. Now, if I chose a point in the intersection, then they're also both in W. And W is a subspace. So that must mean that V1 plus V2 is in W, which means that the intersection, V intersect W, is closed under addition. That's the first thing that I have to show. That is closed under addition, and I just showed it. I picked vectors that were in the intersection, and therefore the sum of the vectors is also in the intersection. All right, what else do I need to show? I need to show scalar multiplication. So again, this time I'm only going to pick one, right? Because I just need scalar multiplication. So this time I'll choose a vector, V1, that's in the intersection of V and W. Well, that must mean that a scalar times V1 is in V because V is closed under scalar addition, scalar multiplication. And now let's choose V1 in W. How do I know that V1 is in W? Well, because it's in the intersection. So if it's in the intersection, it's in both V and in W. Oh, well then C1 V1 is also in W. So it's in V, it's also in W, therefore C1, V1 is in the intersection of V and W, therefore it's a subspace. Okay, so I've shown that if I pick points carefully in the intersection of those two sets, then it is both closed under addition, closed under scalar multiplication. If it meets those two criteria, then it's a subspace. And that's the end of this section.